propagation in tunnel structures at ISM band, a preliminary study. The main goal of our paper and presentation is to make an initial beginning step in understanding underground radio propagation for MRT systems. So this is the overview of my presentation. First I'll start with the background with CBTC, discuss about the CBTC systems. Then I'll discuss about the challenges faced in providing wireless communication in tunnels. And then we'll look into the complex RF environments. What are the complexities which makes the RF environment very challenging in tunnels? Then I'll explain about the radio wave propagation in tunnel-like structures, measurement details, simulation results, and finally we'll conclude about what is the significance of this research. Coming to the background, CPTC, communication-based train control. All the train control operations are managed by the help of communication system. If you look into the fixed block systems, so the location of train is known by using the block size. Usually whenever the train enters a block, then the operator and the train driver knows that he is in particular block. The block size will vary from 1 to 2 kilometers depending on different parameters. Usually the train operators consider 3 blocks, 1 block ahead of the train and 1 block behind the train as the occupied distance. These blocks, this area is not allowed for other trains to enter these blocks. So this problem is overcome by CBTC. What CBTC does is the block distance is dynamically varying depending upon the speed of the train itself and the speed of next coming trains and the operator specifications. One more important thing what CBTC changed in these MRT systems is the train can know its own location. Wherever the train on the track, it can know its own location and it can know the location of the next trains and upcoming trains. According to this information, the trains can make a decision of speeding up or going slow or braking, all these things. So this is possible only by providing a reliable communication system for train all over the track, whether it is in tunnel, in open area, wherever it is. If you provide reliable communication system, then the train can transmit its speed and location information for the next trains, operator, everywhere, and whole system works properly. So this is the radio network in CBTC. Here you can see the access point distributed along the track, and the train is moving here. Usually the trains have 2 antennas, one at the front and one at the back and one at the front. If one loses the link, the other can connect. So as these access points are distributed all over the track, you need to make sure that your train will receive the signal properly all over the tracks. Usually the CBTC systems all over the globe will operate in ISM band, industrial, scientific and medical band, which is license free frequency band. The frequencies in this band are 900 MHz, 2.4 GHz and 5.8 GHz. In Singapore, we are working on 2.4 GHz. The significance of frequency is, as you are going for a higher frequency, the received signal strength falls quickly. Like you just move 2 kilometers more and the signal strength is very, very low compared to 900 MHz. So the main target the main goals of this research is to provide the radio link at different frequencies, independent of where it is being operated. So in this plot you can see, if your train starts at 0 kilometer and it is moving away from this point, let's assume there is a transmitting antenna here which is transmitting 0 dBm power. When you are moving away from the transmitter, the train received signal will be going like this. When the same train is moving inside a tunnel, the received signal is fluctuating highly. Here you can see there are few locations inside the tunnel. The received signal is drastically going down. Few locations, and for most of the locations in the tunnel, the received signal is far high compared to the open area. So these are called deep fades or destructive interference, and these are called constructive interference which enhance the signal. benefit from this constructive interference which enhances my received signal, but the destructive interference will cause a problem. The problem is when your received signal, when your train is not getting this communication link for 1 second to 3 seconds, it will give ATP. Automatic train protection system will be triggered on and the train will break. This is according to CBTC IEEE standards. So when you are speaking about the communication system all over the track, you need to make sure that your train will not lose the signal for more than 1 second, the worst case. So poor signal strength because of changing and complex environment makes the CBTC system very challenging. If the CBTC system fails, and the operator should switch to fixed block for temporary time and then again to CBTC. So these are the complex environments like tunnels of different shape, rectangular, curved, and the complexity is because of different materials used in the tunnels, pipes and metallic structures, shape and size of the tunnel, curvatures of the tunnel, and split points where you have multi-track and single-track. And there are interference scenarios where like tunnels with metro stations in them, tunnels to outdoor, outdoor to tunnel. So as making the real-time measurement inside the tunnel is very difficult because you need to disrupt the train movement there and go into the tunnel and do the measurement, where most of the cases you are not allowed to do that. But we can use the maintenance hours which are in the late nights, and it's very difficult to go into the tunnels and disrupt their maintenance operation. So we can rely on simulation tools, analytical tools. But always the simulation and analytical tools can't perfectly match with the measurement tools. So what we did is, we tried to give a first step in this field by checking at the tunnel-like structures which look similar like a tunnel, like the indoor corridors, the car parking areas, and lift shaft, which have four blocks with concrete materials, similar materials in tunnels. So we thought of doing a measurement and see how it looks and how it matches with the simulation. Then we considered a corridor in NTU, P5 block in S2.2 building. And this is the corridor, which is of length 27.5 meter. And we fixed the transmitter at one point and moved the receiver at 8 different locations along the corridor. So the corridor width is 2.1 and height is around 2.5. And this is the 3D block which we used in the simulation in the corridor measurement. Here you can see the animation of the simulation. Your transmitter is here and the receiver is moving along the corridor. When the receiver is moving along the corridor, you will get a direct signal which is being received, and reflected signal from the walls, floor and roof, and some reflections from this end wall. And there are few reflections from the other end wall, and there are multiple reflections from different regions in the corridor, different areas. So the thing which matches with the real tunnel scenarios is the straight signal and reflection from the walls. So let's see the power delay profile. This is nothing but time on x-axis and power on y-axis, which says how many received signals are there and at what time instant they are being received. So this is at 9 meters from the transmitter. So in the first case, we can see this is direct signal, the line of sight, the direct signal being received, and the reflections from walls, rooftop are seen in the region which is below 100 nanoseconds. Sorry. The second region is this, the reflection from the far wall, the near wall, can be seen in the second region. The third region is this, the reflections from forend wall can be seen here. Finally, we could not match this exactly because we don't know the reflections are from here or not. So from this plot, the information what we get is, in real tunnel scenarios, you are not just getting a single direct signal, but the single direct signal is being influenced by multiple reflection signals by walls and different pipelines or materials inside the tunnel. So we cannot always rely on simulation tools, but it's important to do a measurement and know how many reflected signals are coming and how you can change the power delay profiles. And this is the closer look of region 1. direct path is coming at 18 nanoseconds. The time difference is very less, and the power difference, reception power difference is also very less, which says that at a far away distance like 300-400 meters from the transmitter, the influence of reflected paths is very high compared to the direct path. In this case, from these we said that power delay profile, small scale fading is the big issue, and in this plot you can see the received power of three different size tunnels. Tunnel of size 2.2 meter, 5.5 meter, 8.8 meter is compared. So the reason for doing this is all over the globe we have different size tunnels starting from 3 by 3 to 8 by 8, 10 by 10. So approximately. So the tunnel shape changes continuously. So in this you can see the tunnel of size 2 by 2 meter, which is very narrow tunnel, usually it is in coal mines. The received signal is far more than the open, like free space received signal. We can say that the constructive interference or the multipath effect or reflection effect are increasing the signal strength drastically compared to open space. But when it comes to 5 by 5 meter and 8 by 8 meter tunnels, the reflected path is influencing the direct path a lot, and here you can see there are multiple deep fades. There are multiple chances where your train can lose the signal. So by properly analyzing the overall tunnel structures, by considering their dimension, the radius of curvature, and the height of antennas, you can avoid these deep fades, these deep nuls. You can avoid the chances of losing the train signal for 1 second or more than 1-2 seconds. So this is the conclusion of my presentation. We analyze the wave propagation in tunnel and tunnel-like structure, and then we spoke about the influence of like multipath reflections and wave guiding effects in tunnel structures, and different variation of EM wave propagation with respect to dimensions of tunnel. And in future we want to do the real measurements in the SMRT tunnels, and then we would like to look into the radius of curvature, what is the influence of being slant and slopes on received signal, and how you can solve the how you can make the communication system highly reliable. Thank you one and all. And other than me, Professor Hui Lee, she is associate professor in NTU. She is also part of this project, and my co-supervisor Dr. Yusong Meng, he works in